Hello everybody and welcome to my experiment. I'm trying to see how this works. I do not expect that this is going to get any Academy Awards, but I was hoping that maybe this would help to free us up to do more interesting things in class. So, goal of this lesson is to help you understand nuclear power. It can be a little bit complicated, but we're going to build off of things that we've already learned in class. So we'll dig right in. Now, the first thing that I want you to think about, here are some questions. We've learned all matter is made up of atoms, and we know that at the center of the atom, you're going to find the nucleus, and inside that nucleus, we will have two things. Those are going to be our protons and our neutrons. Back when we learned about radioactive decay, we learned that protons and neutrons are pretty important to giving that nucleus stability. Protons, remember, are the thing that determine what element the atom actually is going to be. So it's the number of protons that determines it. And if you vary the number of neutrons, you're going to get what we call an isotope. So that's just as a reminder of some of the different terms that are relevant here. So let's consider what happens with uranium, which is the substance that we use for nuclear fuel. Here you see two common forms of uranium, U-238 and U-235. Now remember, those numbers are indicating the mass of that atom. So what we see is for 238, it's got 92 protons and 146 neutrons. Remember, what defines it as uranium is 92 protons, so that's why you're going to see the same thing when you look at U-235. What's different? 3 neutrons, so only 143 of them. So that gives them a different mass. As we talked about before, neutrons are important for stability of the nucleus. And so having a different number of neutrons can lead to instability. As it turns out, both of these forms of uranium are not completely stable, and therefore we're going to call them radioactive. Remember, when they're radioactive, that means that the combination of protons and neutrons isn't capable of holding the nucleus together for too long of a period of time. Eventually it will break down and go through decay. And that's why we call them radioactive materials, because they're decaying and giving off radiation. So do remember that the amount of time that it takes for that radioactive decay to take place, for 50% of those atoms to go through decay, we call that a half-life. Now, we're going to go into a little more detail here than we did the first time when we went through this for radioactive dating. What we're going to talk about is how there are some common patterns to how radioactive decay happens. And so we're going to look at some of those. One of them is called alpha decay, and you see that when you look at uranium-238. So U-238, when it breaks down, you can see that it emits a helium nucleus. What we have are 2 protons, 2 neutrons, and as a result, that's the same thing you'd find in a nucleus of helium. The net result is we've decayed it down to a daughter element that is smaller, has less mass, and in the process are giving off energy and radiation. So that's what's taking place when you have alpha decay. Alpha decay gives off that helium nucleus, and it's going to give off it's going to be ionizing. It's considered ionizing. And the reason why we call it that is because it's capable of moving electrons and therefore rearranging chemical bonds. We would say that it's not very penetrating because a helium nucleus is pretty big. So as a result, it's going to be stopped by when it runs into other matter. So for example, a sheet of paper will be able to stop a helium nucleus. So while it is ionizing, it is not very penetrating. It will not go through things very far. Now, another type of decay that we see commonly is called beta decay. And beta decay can happen in 2 different ways. We have beta minus decay and beta plus decay. And what you notice is, if you're looking at the diagram, you're going to end up with slightly different things. So one is a neutron splitting into a proton and electron, and that's going to eject an electron out. So what we see is that the nucleus ends up gaining a proton in the process and does not change its mass because it still has mass-bearing particles there. When we look at beta plus decay, a proton is going to combine with an electron to become a neutron. And what we find is it's going to have to give off a positron, a positively charged electron-like particle. The nucleus ends up losing a proton, but there's no change in mass also. So no change in mass when you have beta decay. And one more thing about beta decay is that it is changing the number of protons. So therefore, it is changing what the element is. And so if you recall back when we learned about carbon-14, carbon-14 decayed into nitrogen-14. That's an example of beta minus decay because you went from having 6 protons and 8 neutrons to 7 protons, 7 neutrons. That's beta minus decay. So you can see we've already learned some examples of this. We just hadn't talked about what was really happening. And so these are common patterns that many different radioactive elements show. So with these different types of decay, you get different effects of the radiation. As we've already mentioned, an alpha particle is going to be given off from alpha decay, and those are going to be a helium nucleus. It's not very penetrating as it shows in this diagram here. But as you can see, beta particles are going to potentially penetrate through your skin. And as it says, could be stopped by a layer of clothing or a few millimeters of a substance like aluminum. But other types of radioactive decay can give off things like gamma rays, and those are going to potentially be much more penetrating, but not necessarily ionizing, because after all, they're going to be moving through things and therefore not interacting with electrons, and therefore not going to be ionizing. What we think about, though, is that these particles with higher energy and ionizing radiation, those are the things that make nuclear power dangerous, and nuclear materials, I should say, dangerous. When you hear about a nuclear accident and why it would still be dangerous after long after the explosions have happened, you would be dealing with decay of radioactive substances, and that means radiation and particle emissions. So those are the dangerous things. So when we think about what is actually used in a power plant for nuclear power, we've already learned that carbon-14 is radioactive. But can you run a power plant off of carbon-14? The answer is no, because when you think about what carbon-14 is, it's got its own half-life that is 5,730 years. I mean, you're not going to be capable of waiting around for that to happen. So you need certain types of materials, so you cannot use just anything. What you need is something that's going to provide you with more energy. And so you can't just go with typical breakdown of a radioactive substance. So what do you need? You need something called fissionable material. And so here's what fissionable material is. It's something where you can induce radioactive decay by hitting the nucleus of the atom with a high-speed neutron. So if you collide a neutron with that target nucleus, you can cause it to go through fission and speed up the process in a sense. So these atoms, these are things that are called fissionable substances, and fissionable substances would be a requirement for a nuclear power plant. But not only does it have to be fissionable, but you also need to take it to another level, because fissionable material, it will only provide that little bit of energy because you've hit it with the neutron. You need something that's going to be able to have a multiplying effect, and we call that a chain reaction. And so if you look at the diagram here, you can see what we mean by a chain reaction, that the neutron hits into one, which splits and releases its own neutrons, which hits others, which then repeat the process. And as you can imagine, if each of these are releasing energy, the amount of energy that's being released is being multiplied as time goes on. And this is going to be happening very rapidly. So if it goes that rapidly, you might say, well, eventually it's going to be way too much energy. And that would be exactly correct, because that's exactly what happens in a nuclear weapon. So nuclear bombs are based upon the idea that a tremendous amount of energy is released from a chain reaction, and it gets so much that it just explodes. You obviously don't want that to happen in a nuclear power plant, so you must control the reaction. And the way that we found is an effective way to keep these reactions under control is using something called nuclear control rods. And so, as you can see here, these nuclear control rods can be lowered down into the reactor where they can absorb some of those neutrons. If they absorb them, then they're not freely moving around to collide with other nuclear fuel, and therefore not causing more of the chain reaction to happen. So it's a way of limiting the chain reaction so that it doesn't go out of control and lead to an explosion. So this is an essential component of all nuclear power plants, and it allows us to manage the nuclear power and keep it under control so that we can do useful work with this. That wraps it up for the first segment of this, and I hope that you learned a lot about the way that nuclear materials are working in terms of the common ways that we go through radioactive decay, and the fact that it's certain isotopes that have the right characteristics so that we can make them fissionable, and that they are not only fissionable but also fissile because they can go through chain reactions. Thank you, and hope you enjoy the next segment too.